you see my screen?
Yes. Hello,
Yeah.
everyone. Hi, everyone, and welcome to today's seminar of bioelectronics. Today, we are very happy to have Minkyu Lee from Northwestern University. He's received his PhD in material science and engineering from Seoul National University, where his work focused on functionalized biomaterials. He subsequently completed his postdoctoral training in bioelectronics with Professor John Rogers at the Query Symbion Institute for Bioelectronics at Northwestern University, where he was developing wireless, battery-free, miniaturized, fully implantable bioelectronic system. He is currently a postdoctoral fellow at the Shirley Reliability Lab at Northwestern Medicine, where he worked with Dr. Monica on neurorehabilitation after spinal cord injury. His research vision integrates implantable materials, bioelectronics, and rehabilitation applications. So we are today very happy to host Minkyu with us. He's going to give us a talk on an integrated bioelectronics platform for probing in vivo neuropharmacology. And before we are going to the talk, I just want to remind everyone, if you have any question, please drop them in the Q&A box or raise your hand and we can take all of the questions by the end of the talk. And with no further delay, I would say thank you first, thank you for being with us today, and the floor is yours.
Thank you very much. It is my great pleasure to be here today for the part of BioElevated seminar series. And special thanks to Latifa for kind invitation and arrangement of this talk. Thank you very much again. My name is Minkyu Lee. I'm a postdoc fellow at Northwestern University. I was previously in Professor Johnny Rogers' lab at Northwestern University. My work focused on creating tiny brain implant, which I will present today. Then I moved to the Shirley Reliability Lab, which is rehabilitation hospital of Northwestern Medicine. Now my work interests in focusing on applying brain stimulation technology to the human, especially for individuals with spinal cord injury. Yeah, today I want to briefly introduce one of my recent work, an integrated bioelectronic platform for probing in vivo neuropharmacology, which recently published in Neuro. Right. In today's talk, I want to go over the context and motivation of this integrated bioelectronic platform. Then I want to introduce the device, integrated bioelectronic platform, and I will conclude with some future work and the summary of this work. All right, before going to the detail of the device bioelectronic system, I want to give you a little context of neurological disorder. As we already know, neurological disorders such as drug addiction, depression, anxiety, spinal cord injury is a leading cause of disability and second common cause of the death worldwide. And we have technology to better understand and treat these neurological disorders. As we already know, we try to better understand neurological disorder by sensing and try to better treat neurological disorder by neurosimulation. Sensing consists biopotential sensing as neuron potential, and we optically monitor brain or neural circuit. For the stimulation for better treatment of neurological disorder, we apply electrical stimulation to the nervous system, or we deliver a drug to cure this neurological disorder. These are existing technology to better understand and treat neurological disorder. And among these neurological disorder, today I want to more focus on neuropsychiatric disorder, and then especially neuropharmacology. So before we talking about neuropharmacology, what's the neuropharmacology? Neuropharmacology is a research area that study how drugs affect the nervous system. So let me give you an example in our daily life. For example, how Tylenol affect the nervous system to reduce the pain signal. That's one of the example in our daily life for neuropharmacology research. And another example is how caffeine affect our nervous system. As we already know, caffeine drives us to do science, right? Caffeine drives us to prepare manuscript. Caffeine drives us to prepare grant proposal. So caffeine drives us to do science. So we already know how this neuropharmacology works in our daily life. For example, Tylenol and coffee. So one of the widely used tool for neuropharmacology research, how drugs affect the brain, is cannulation. These are overview of cannulation technology. We have mouse here, and this external syringe pump supply drug through this metal tubing, and this drug delivered through this bulky metal tubing implanted into the mice brain. So cannulation allows us to directly deliver the drug to the neurons and neural circuits so that we can study how drug affect the brain, which is good. However, when you take a look closely for this cannulation system, there's several limitations. First, cannulation system cannot monitor neural activity. That means we can deliver drug to the region we want. However, we don't know what's going on in the brain because we don't have sensing capability in this cannulation. Second, we cannot pinpoint neurons and neural circuit. Yeah, think about the size of neurons and neural circuit. It's very tiny. And then think about the size of this bulky metal tubing. With this size mismatch, it is hard to pinpoint neurons and neural circuit for the research. And most importantly, we cannot deliver multiple drugs at the same time. As you already know, there's a certain drug have interaction with other drugs. For example, when you're sick, when you take Tylenol, there's a certain drug you should not take with Tylenol because they have an interaction. To study this interaction between two drugs, we need to deliver multiple drug to the neurons and neural circuit. However, as you can see from this picture, this external syringe pumping system has a single drug reservoir, which doesn't allow us to deliver multiple drug at once. So altogether, current cannulation technology use indirect method due to the technical limitation. I just talked about this cannulation approach, and then there's some also approach which eliminate the need for external cable. This is one of the example bulky battery-based wireless system. This system is great because we don't need any external power cable, which can limit animals' natural behavior for drug delivery. However, when you take a close look for this system also quite heavy. So you cannot incorporate it, optical imaging capability to see how drug affect the brain in real time. So this is current limitation of technology to study neuropharmacology. So central research question here is that how can we better understand how drug affect the brain? How can we overcome these technical limitations? The core technology to overcome these limitations in the field is near-field communication. Near-field communication, which called NFC, is widely used wireless technology in our daily life. For example, how you pay at the restaurant with this wireless technology, and how you wirelessly charge your iPhone. When we apply this NFC technology, we can create tiny device which doesn't require external cable to supply power to the system. This is a schematic diagram we have animal here, and this tiny brain chip implanted into animal's brain. And this tiny device has coil around, which can wirelessly harvest the power from this animal cage with the coil antenna. This system, as you can see from the imaging, this can be wireless. This can be battery-free. Since it doesn't require battery or any extra external power cable, we can significantly decrease the size of the device, which could be even lighter than 0.2 gram. And also, you don't need to charge the device frequently, or you don't need to replace the battery. This system can allow us to perform research in uninterrupted and long-term manner. So I'm gonna leverage. I have applied this NFC technology to create tiny brain chip that allow us to better understand how drug affect the brain. Let me show you how we made this possible. So now I'm gonna briefly introduce the tiny system on integrated optical microfluidic platform. This is a schematic diagram of the device. I'm going to explain layer by layer the function of the device. Okay, at the bottom, we have electronic components. These electronic components allow us to communicate between this wireless device with your mobile, tablet, PC, or phone. And as I just mentioned in the previous slide, this device has coil antenna, which allow us to harvest energy wirelessly from the animal cage, which allow us to decrease the size of the device significantly. And we have electrolyte chamber, which is driving force for drug delivery. And we have flexible polymer membrane. I'm going to explain the principle of operating system later, more detail, and most importantly, we have multiple drug reservoir. Previous system for the cannulation, we have only single drug reservoir. In this system, we have multiple drug reservoir, allow us to load different type of drug in the same device for neuropharmacology research. And this drug transport through this microfluidic channel, and it delivered to the imaging area. That means, what does that mean? We're delivering this drug to the imaging area. That means while monitoring brain activity through this integrated optical fiber implanted into the brain, we deliver the drug to the imaging area. That means this system will allow us to monitor how drug affect the brain in real time. So actually, it was not easy. It was a long journey to create this tiny integrated system because, as I mentioned earlier, we have to gather around many different aspects of engineering. For example, we need to think about soft, flexible, biocompatible materials from material science aspect. And also, we have to think about power efficient circuit for miniaturize this electronic system from electrical engineering and wireless communication for the coding, computer engineering. And we need to think about how can we reliably and safely deliver the drug to the brain from this microfluidic dynamic aspect. So we have to gather a interdisciplinary team's effort to create this tiny wireless micro pumping system, which is lighter than 0.15 gram and smaller than your fingertip. The key feature of these devices, as I mentioned, this device can be wirelessly charged without any need of battery or external cable. And this device has soft, flexible microfluidic channel, which integrated into the optical fiber for imaging. And also, not only just delivering the drug, this device has multiple drug reservoir, which allow us to programmably deliver multiple drug That means we can activate drug reservoir 1, 2, and then how fast drug delivery we want. So we can control operating parameters such as duty cycle, power, so that we can deliver the drug to the rate we want. Yeah, long story short, our team replaced this current bulky external syringe pumping system with bulky metal tubing into tiny integrated platform, which is lighter than 0.15 gram. This is the scale as of on the fingertip, but not only decreasing the size of this drug delivery system, we also integrated one more function, which is imaging. So this system allows us to monitor how drug affect the brain in real time. So previous system, we weren't able to monitor neural activity because we don't have sensing capability. But this integrated platform allows simultaneous drug delivery and neural recording. And also, this system use tiny microfluidic channel in the diameter of 10 and 30 micrometer, which is definitely smaller than previous cannulation system, 100 micrometer. Now we can pinpoint neurons and neural circuit. And most importantly, this tiny system will, with multiple drug reservoir, allow us to deliver multiple drug compounds to the within a single platform. So altogether, this integrated micropumping system enable direct observation of drug-neuron interaction. So let's see how this tiny device works. This is a cross-section of this micropumping system. So at the bottom, we have electrode, which is gold and copper, and this electrode is in contact with electrolyte in electrolyte chamber. And this red color is drug reservoir, and this drug reservoir and micro pump chamber containing electrolyte is separated by flexible polymer membrane. So when wirelessly harvested power applied to this electrode, which is in contact with electrolyte, it initiates electrolysis reaction, which converts water to oxygen and hydrogen bubble. So when this electrolysis reaction creates oxygen hydrogen bubble, this created bubble push the flexible membrane, which is driving force for the drug delivery from the drug reservoir to the microfluidic channel. This released drug from the drug reservoir transport through this attached microfluidic channel, and then eventually we can deliver this drug to the region of our interest, which is tip of imaging fiber, so that we can monitor how drug affect the brain in real time. This is the operating principle of this electrochemical pumping system for reliable drug delivery. Since we use electrochemical pumping system, this system requires lower power compared to the mechanical pumping system, or also produce negligible noise or vibration, which allow us to stably monitor neural activity during this operation. This is what we want, and this is what we don't want. Delivering drug to the region of our interest is very important. So we want to deliver the drug to the right spot, not just random spot. So we made sure this integrated microfluidic system delivered drug to the targeted area, to the imaging fiber. We run the mechanical simulation in the brain tissue model. On the left, this is a bottom of the fiber, and the fluidic outlet is attached on the top of bottom of the fiber. And on the right, the red color And number 1 means 100% concentration of the drug, and the blue color 0 means 0 concentration of the drug. As time goes on, from 1 second to 25 seconds, as you can see, after operating this micropumping system, this fluid system was able to effectively and rapidly cover field of view without off-target effect within 10 to 20 seconds. So from this mechanical simulation, we were able to make sure our system reliably and safely deliver the drug to the targeted area without off-target effect during imaging. So let's go back to the central question. So why do we need this device? The reason why we developed this device is we wanted to know how can we better understand how drug affect the brain. For example, how does dopamine affect the brain? As you already know, the use of drugs such as cocaine, opioid, morphine, this caused a very serious problem in the society, and these drugs increase the level of dopamine in the brain. So if we can better understand how this dopamine affect the brain, we will have better understanding of what kind of treatment and what is the mechanism underlying this neuropsychiatric disorder. So we weren't able to answer this question because we don't have technology. The current cannulation technology has several limitations. So we have limited understanding of how does drug affect the brain, how does dopamine affect the brain. But now we can answer this question because we have device. We have device allow us to answer this question to better understand and treat neuropsychiatric disorder. So now I'm going to show you an example. Now I'm going to show you animal data, how this device operated in animal model, and how it help us to answer the unanswered question in neuropsychiatric disorder research. In this animal test, we try to answer two main questions. So first, how drug affect the brain? For example, how dopamine affect the brain? That's the first question. And then not only that, how different concentration of the dopamine affect the brain? As I mentioned earlier, this tiny microfluidic system has multiple drug reservoir. That means not only loading the single drug compounds, we could load different concentration of the dopamine in these two micro drug reservoir. So we can answer this question within single platform with this integrated bioelectronic system. I'm going to show you the animal test video. But before showing you a video, just wanted to give you a sense. We express two biosensors to capture the level of dopamine and level of kappa opioid receptor. The purple color line here is RGRAP-DA sensor, which tells you the level of dopamine in the brain. As you know, dopamine is related to positive emotions such as pleasure and reward. And K-light activity was shown in white color in this graph. This K-light biosensor detects kappa opioid receptor level. This related to the negative emotion, such as stress and anxiety. Okay. In the left side video, we deliver lower concentration of the dopamine into the mice brain. And for the recording, fiber photometric recording, we still need to connect the patch cable, but this micropumping system is completely wireless. We deliver lower concentration of dopamine, and then we deliver higher concentration of the dopamine. So when we deliver lower concentration of the dopamine, from this graph, we were able to monitor immediate increase in dopamine level, which show in purple color in our graph the ape. However, K-light activity was pretty much stay in the same level as the baseline. But very interestingly, when we deliver higher concentration of dopamine, of course, we were able to monitor immediate increase in dopamine level, but we also able to monitor significant reduction of K-light activity, which we weren't able to monitor in case of lower concentration of the dopamine. So what does that mean? That means type of drug important, but also concentration of the drug is also important, because as you can see from this image video, we were able to monitor how this different concentration of the dopamine create different neurodynamics. So it will give us better understanding of the concentration dominant effect to the neuropsychiatric disorder and underlying mechanism. So long story short, from this validation, this system has multiple drug reservoir, which could load different concentration of the drug, or it could be different type of the drug. And this system, integrated system, also have optical fiber, allow us to monitor brain activity in real time. And not only that, we can also monitor behavior output. As you can see from this heat mapping data, before delivering dopamine and after delivering dopamine, you can see mice running around the cage very fastly. So by using this system, we can deliver multiple compounds and also monitor how this drug affect the brain, and also monitor how this brain activity makes some behavior output, and we can correlate these physiological and behavioral outcome within a single platform, all in one in real time. This is an example of how this new platform advanced our understanding on neurological disorder. Yep. So in conclusion, we wanted to better understand how can we better understand how drug affect the brain. However, current cannulation approach has some limitation. So to better understand this, we created tiny system which allow us to simultaneous drug delivery and imaging within a single tiny platform. And this work, proudly, we were able to collaborate with outstanding neuroscientists at University of Washington, Professor Brukas Group. Professor Brukas is the pioneer in neuropharmacology research and dopamine addiction, and also Dr. Piantadosi, who is a co-first author of this paper. He's an outstanding neuroscientist apart from this animal validation works. And now he's the incoming assistant professor at UC Irvine. And Dr. Wu at Curie Simpson Institute for Bioelectronics with Professor Jenia Kojorovsky. He performed feasibility validation and improvement of device functionality. And of course, huge support from Dr. Rogers, and also a spin-out company from Curie Simpson Institute for Bioelectronics, neurologs, Dr. Banks and Good for technical support, and Dr. Huang and Raudel for mechanical simulation of microfluidic dynamics. So it was interdisciplinary, huge teamwork. So I appreciate the collaborator and mentor who made this possible. And thank you very much. And I'm happy to take any question you may have. But thank you for your time.
Thank you very much, Minkyu. It was really nice talk, and like indeed, the optical imaging is very important for the in vivo, and like it's very nice work that you have done. So a kind reminder for everyone, if anyone have any questions, so you can raise your hand and we can enable your mic, or you can write them on the Q&A box, and we can take the question. I can read it to Minkyu to answer. So yeah, it's the time now to ask any question if you have any. So maybe I can start with some few questions. So I'm curious about the microfabrication part of the whole system, actually. So first question is about the microfluidic channel itself. Like, which material do you use, and can you like comment about like the long-term stability for chronic application? Like, yeah, in terms of fab, also for the whole system.
Yeah, of course. Yeah, that's a great question. So, for microfluidic channel part, we use
Yeah.
classic PDMS.
Oh,
So,
okay.
yeah, it's a classic PDMS, but for the chronic stability of device operation, that's a really good part.
Yeah.
I mean, in terms of biocompatibility, as you already know, PDMS is bioinert, so we don't really
Yeah.
experience any big issue. However, to clogging it was the issue. You know, if you want to deliver the drug, for example, every week,
Yeah.
that it is hard to achieve with the current system. As you
Oh,
already
yeah.
know, after
Yeah.
implanting this microfluidic channel probe into the brain, the blood penetrates into the fluidic channel
Yeah.
outlet, and then it dries out, and also like some fascia growth and
Oh, yeah.
tissue chunk. So it prevents drug delivery in a
Yeah.
chronic manner. So uh, this system operated in pretty much acute setting. So that would be the future work definitely to improve chronic stability of drug delivery in like weekly basis.
That's nice. Okay, that's cool. So, what is the size now for the outlet of the drug delivery? And you still observe like some tissue formation after implantation?
Yeah, so the size of outlet was 30 micrometer, 30 by 30.
Okay.
30 by
Oh, 30
30.
by 30. Yeah.
Yeah, and then as you already know, after implantation, we were able to see some, blood, with the capillary
Mm.
force, blood penetrate into the microfluidic channel and
Oh,
dries
to the
out,
channel
further clogging.
itself.
Yes,
Interesting.
yes.
Yeah.
Mm.
Okay. That's interesting to know. Yeah, that's cool. Yeah, so yeah, it's very interesting, and yeah, indeed, it's very challenging to like deal with the chronic
Uh,
application. Yeah,
mhm.
so yeah, and like, what about like the back end side of the thing, like the thing that is not implanted? Do you see it like very stable, or like do you have some delamination issue or something like that?
Yeah, device itself is very stable. We can implant and we can I mean they can stay for several months with no
Oh,
issue
nice.
because
Okay.
this is a flexible printed circuit board system with
Yeah.
encapsulated by PDMS and other encapsulators, so it's very uh, stable. But however, the
Mm-hmm.
one challenging could be, mouse scratch, try to scratch all the time.
Oh, yeah.
So
Yeah.
yeah,
Exactly. Yeah.
sometimes we use some 3D printed protective cap
Okay.
to avoid this, device failure from the scratch. But other than that, it can stay for several months with no issue. Device connected well after several months of implantation.
That's very nice. Yeah, that's very nice to know. And like, so you don't do electronics on the microfluidic channel itself, right? Because I think BDMS doesn't have good adhesion with the metal, no? So do you have separate channels for like, yeah, as you said, like there's the membrane, and then below it, you're using which type of material for the electronics?
Yeah, yeah, we don't have any like metal or rigid proof
Yeah,
combined with the fluid channel. Just this mic
yeah.
PDMS based microfluidic channel directly attached to the optical fiber with the
Mm-hmm.
glue. Yeah.
Okay, with a glue. Is
Yeah.
standard UV glue or
Yeah, just epoxy,
just a
not
box? Okay.
nothing special.
Yeah. Okay. That's very interesting. So if no one has any further more question, maybe we can close up for today. And thank you again, Minkyu. It was really interesting talk and like really nice work as well. Thank you everyone for attending with us today, and we are going to have our next seminar in the next 3 weeks, and we will send the invite and about the next speaker soon via email, also in our LinkedIn page. And until then, I would say thank you everyone, and we will see you soon in our next seminars.
Thank you very much.
Thank you. Thank you. Bye.